one very good example of such a problem that I have been studying recently is the problem of understanding the structure of translational tilings. So I thought it would be nice to share this field of research with you. So Simone yesterday talked about tilings as well. Today we will restrict our attention to very special type of tilings where we allow only translations and we tile by only one tile. So to be more precise, I'll start by defining translational tilings in the Euclidean space. Here I consider some bounded measurable set omega in RD, and I ask whether there is any countable set T such that if I will translate my set omega along the points of D, I will cover almost any point in RD exactly once. If this is the case, if I can find such a T, then I would say that omega is a tile of my space RD, and T would be a tiling by omega. This is the terminology that I'm going to use. And here are some examples or that illustrate planar example that illustrate this notion. And I want to turn your attention to the fact that in each of these examples, the tiling is along a lattice, where I say, by a lattice, I mean a subgroup of RD whose quotient is compact. So this is the object. These are translational tilings in Euclidean space. And the general question that I want to study is analyzing the structure of such tiling. Or if I denote, I use this orange notation for the set of all the tilings by omega, I want to understand what this space looks like. This is the general question, and let's see some examples. For example, if my set omega is a symmetric hexagon in the plane in R2, then the space of the tiling consists of just one lattice and all its cosets, so it's unique up to translation. However, if when I wanted to tile my backyard with a rectangle, this was no longer the case because I had the freedom to shift independently the rows. And more generally, I can consider cube tilings in all dimensions. And cube tilings, one might consider them as trivial translational tilings or naive tilings. But it turns out that in higher dimension, the structure of this tiling gets extremely complicated. And just to demonstrate this phenomenon, I will ask you a question. Does any cube tiling contain two cubes that share a common facet? So the picture here hints that the answer should be positive, at least in 2 dimensions. And Keller conjectured in the 30s that the answer is positive in all dimensions. But after a lot of work, it took more than 60 years until a counter example were constructed to Keller's conjecture in dimensions 8 and higher. Using graph theory and group theory method, the story is really fascinating, but I will not be able to tell you the story today. By the way, the conjecture is known to in dimension 1 to 7, and this is a different story, which is interesting. But I'll be able to talk with you afterwards. Anyway, so this we kind of, I hope, get a feel that the question about the structure of tiling is highly non-trivial. And perhaps the most well-known conjecture in the area is the periodic tiling conjecture. This conjecture asserts that if my set omega is a tile of RD, then it admits a periodic tiling. Namely, if this space of solutions or tilings is non-empty, then then it must contain at least one set that is invariant under translation by some lattice. This conjecture was implicitly posed in 1987 by Greenfeld and Shepard, and a bit later it was explicitly formulated by Lagares and Wan in 1996. So let me tell you some of the main results with regard to this conjecture. So when Kopp and McMullen proved that the conjecture holds convex domains in all dimensions using mostly geometry, Lagares and Wan proved the conjecture in dimension 1 using Fourier analysis. Buquier, Nevat, and later Kenyon proved the conjecture for topological disks in the plane using geometry and topology tools. And this is more or less it. So we don't know much about this conjecture in the Euclidean space. Let me then try to restrict our attention to just tiling of the integer lattice. So here, my tile would be a finite subset of ZD, such that I can partition ZD into translates of this finite subset F. And I will adopt this notation as before for the set of all the tilings of ZD by F. Let's see some examples. So here is a simple example. My F is a singleton, contains only one point. Then this is a tile of ZD, because if I translate it along the integer lattice, I cover every point in the lattice exactly once. I have a tiling. And in fact, this is the only tiling by a singleton. Here's another example. Now I want to tile Z by its subset, the set of the points 0 and 2. So I'll put one copy at 0, and then another copy 1 at 4, 5, 8, 9, and I will continue like this, and you can already probably believe me that this green set solves this tiling equation. So this F is a tile of Z, and I want to just notice that this green set, the tiling set, is not a lattice, but it is periodic. Now, so far we have seen just examples of sets that do tile by translation, and of course that this is not always the case. So here is an example where we cannot tile the space. If I take the subset of Z, the set of the integers 0, 1, and 3, I will not be able to tile Z by translations of this set, because, for example, there is no way to cover the point 2 without overlapping. Okay, so these are some examples, and under the continuous setup, I can also here ask the question about the periodicity of tiling, to formulate the discrete periodic tiling conjecture, which suggests that if F tile ZD, then it admits a periodic tiling. So now I want to convince you that it's actually useful to try to study this conjecture. And one reason why it might be useful for us to try to study this conjecture is the fact that if we found a counterexample to this conjecture, then we get the failure of the continuous periodic tiling conjecture. Let me show you why. So of course that if I have a tiling in the discrete setup by F, by a finite subset F, if I replace any point of F by just a unit square that is centered at this point, I get a tiling of RD. This is clear. The problem is that I might, in RD, I have more degrees of freedom. And if I do that, I might obtain too many solutions here that do not correspond to the solution that I had here, to the tiling that I had in the discrete setup. So what I do to prevent this situation, I will replace the unit cube with a jigsaw puzzle, which would not allow me to slide anything. And if I do this, then I get that the tilings in the discrete setup are the same as the tilings in the continuous setup up to translation, but translation don't change the periodicity, so I don't care. And that is why the continuous periodic tiling conjecture implies the discrete periodic tiling conjecture. Another reason why it's useful to study the discrete periodic tiling conjecture is its connection to the decidability of tiling. Or the question whether there exists an algorithm such that upon any input of finite subset of ZD, my algorithm would compute whether this is a tile or not. And Hawan showed that in the 60s that if the discrete periodic tiling conjecture is true, then we have the decidability of tiling, which is useful. So there are good reasons to study the discrete periodic tiling conjecture, and indeed many researchers invested a lot of time and efforts to try to understand this conjecture. And let me just show you some of the main results that were obtained. This is just a partial list. The one-dimensional case was solved by Newman by his simple pigeonholing argument. Newman proved that the conjecture holds in Z. The two-dimensional case is already quite complicated, and it was solved only very recently by Bhattacharya using the ergodic theory method mostly. And we were able to, in 2020, to simplify the argument, or to suggest an alternative proof for this result with Terita. And in higher dimension, Szegedy proved that the conjecture holds for tiles of prime cardinality or cardinality that is equal to 4. Using combinatorial and number theoretical techniques.
Can you say one iota as to how he would use its prime?
Sorry?
How could you possibly use that the set's got prime size?
You go to frequency space. That's where it becomes useful.
Meaning you take Fourier transform?
Yes. I didn't mention it here, but you can reformulate the tiling condition using convolution. And therefore, it's very useful to take the Fourier transform and you get a product equation in frequency space. And sometimes it might be useful to study the problem there.
Yeah, and being prime makes what happen?
Yes.
What happens when you prime on the frequency?
You need to study vanishing sums of roots of unity. Okay. So we will have a redistribution. Okay. So in an upcoming paper with Terry Tao, we construct a counterexample to both conjecture, the one in ZD, the discrete one, and the continuous one. And in fact, our construction is based on a construction in Z2 cross a finite abelian group, which suggests or hints that the conjecture should fail quite early in terms of the dimension.
What D do you have, Abby?
Sorry?
What do you have an effective value for D?
Yeah, we have an effective, but it's used. What we do, we just pull back. We take the construction that we had in Z2 cross G naught, and we pull it back. So we get like an enormous D, but this is the question that I was about to ask. What is the optimal D? Where exactly the conjecture start to fail? The continuous one and the discrete one, we can ask the same question. Another interesting question, I showed you that the continuous periodic tiling conjecture implies the discrete periodic tiling conjecture, but what about the converse? So the converse is now too cold in dimension 1 due to Lagarison 1, but this is open in higher dimension, and this is a question that we currently study. Another question is about the decidability. The periodic tiling conjecture fails, but what about the decidability? Are there any undecidable tiling problems in ZD? We don't know. And maybe the most interesting question is to try to use our techniques to better understand other long-standing tiling-related problems, such as the Nivat conjecture and the Copeland-Mayorich conjecture. I will not be able today to tell you more about these conjectures, but I'll be happy to talk with you anytime. Thank you.
Questions?
Can you repeat the Zegady's theorem? Is in any dimension that if f is prime,
Just a cardinality.
then it's true.
Mhm.
Wow.
He also suggests an algorithm based on his result. He tries to write a good, an effective algorithm to actually.
So you mentioned continuous conjecture is false for D8 and onwards, right?
Yes.
But for the discrete one, you don't know what is the optimal D at all.
No, the Taylor's conjecture is different in nature than
So one implies the other. The continuous implies the discrete, but not the other way around.
Yes. Yes. But to ask about Taylor's conjecture.
Right.
Yes. Taylor's conjecture is a question about cube tilings. There it was after a lot of effort. Actually, the 7-dimensional case was solved when I just arrived to UCLA in 2019 using computer. So it is a computer assisted proof. That is why decidability might be very useful to tiling related questions.
Is there a random question that can be asked? So I don't know, look at all the tiles that are in the box and have, I don't know, at most this many points. How many of them are tiles? Say all the sets, how many are tiles? And of the tiles, how many of them are periodic tiling? Is it generic to be?
What I can say, I didn't try to look into this question, but my feeling is that if you take a generic tile, you would get probably a rigid tiling.
Or unique?
So, yeah.
That makes sense.
So you would expect that there is, generically, there is a tiling. Like for a generic tile, it can tile the...
Oh no, most of the time we will not tile. Tiling is a very extremely special property. But if we have a tile in like a generic tile among all the set of two tiles, a generic tile would admit only rigid tiling, but will have some uniqueness.
The tile that you construct in the convex sample, does it have a unique tiling or not?
The tile that we construct is actually not, the construction is not, is indirect. So we first replace the question about functions, and then we kind of encode using tiling equation function that has a non-periodic nature. And we make sure that all the solution to this system of constraints will be of this type, will not get good solutions. So it's hard, we don't actually, at some point we lose the connection to the structure of the tile or the tiling. I would say that it depends on the definition of rigid. We will get, it will not be unique. It will not be unique, but it will have a very special, all the tiling will have a very special structure.
The tile you construct, what size is it? Can you compute the size?
Fine.
We can compute the size.
Cannot be prime.
Yeah, it's not a rhyme. We can compute it, everything is effective, everything is computable, but we didn't actually try to go ahead and try. We don't know even what is the structure of the tile that we get. It's interesting because if it has nice structure, we get better results. But we didn't try to
Okay, so I guess we can go to T, thank our speaker again.